So, immediate corollary to the above characterization of nilpotent operators we approved, I will note that immediately. In this is now the matrix. If a matrix, square matrix, A is a square matrix, is nilpotent, then already A power n is 0 and A is similar to an upper triangular matrix with diagonal entry 0, with all diagonal entries zero. This is immediate from the above because matrix A, you can think of a linear operator Fa, and if this is nilpotent, the linear operator is nilpotent, and then we found a basis whose matrix of this linear map is an upper triangular matrix with diagonal entry 0, but this was a matrix of this with a standard basis. I have changed a basis. So, the two matrices will differ by a similar, therefore, this is obvious from the earlier part, and the fact that if you have a linear map and if you change a basis of a vector space, the two matrices are related, they are similar. That is why. Okay, now let us, now I want to define elementary matrices. So, these elementary operations. And remember, they were elementary operations which were involving rows and columns. And on there are three types of operations. One is adding a multiple, a scalar multiple of one row to another row. 2 is multiplying any row by a non-zero scalar. So, multiplying any row by a non-zero scalar, and third was interchanging two rows. And similarly for the columns, and I want to set up a notation for this. So, for that let me remind you that we are now working in MNK, or more generally MNK. So, matrices with m rows and n columns. So, let me remind you that here we denote En is the identity matrix, and also here E, I, J, these are so called matrix units. That says ijth entry of the matrix is 1 and all other entries are 0, and that makes sense for any arbitrary m cross n matrix. And this is a basis for this vector space. This is a vector space of dimension mn, and this where I varies in between 1 and m and j varies in between 1 and n. This is the basis of this vector space. In this case, actually this is an algebra. So, these are Also the units and this now 1 and j, they are varying in between 1 and n. I and j varying between 1 and n. So this is a vector space of dimension n square, and all this multiplication is determined by how I multiply Eij with Ekl, and this we saw last time what it is. This is again a matrix unit. This is again E. This is only no, this is delta j k il. This is this. Okay, this is very simple to check. We saw it last time also. So that is how the calculation, I will make calculation either here or here. So, the and also when I make elementary operations on the matrices, I will prefer to use 1 maximum. I will avoid using 2 and 3 as far as possible. So, for the operation 1, what we are doing is, so the matrix corresponding to that will be, I will denote B I j inside the bracket A. So this is defined for 1 less equal to I less equal to m, and 1 less equal to j less equal to n, and arbitrary scalar A. And what are we doing? In this, if you want to write in terms of row operations, ith row is replaced by to Ri you add j times a times the jth row. That is how this matrix is by definition identity matrix En plus A times Eij. This is the definition of elementary matrix. So let us do it for square matrices first. So I am assuming m equal to n. So these are done only for m equal to n. Is that clear? Sorry to make a confusion. I am working in the square matrices. For there, any two indices I and j and any scalar, I will define this matrix to be identity matrix plus Eij. That means only one, this is the identity matrix, once on the diagonal, and at somewhere, some place where I is not j, there is a entry A, and everywhere else it is 0. This entry is at ith row and jth column. This is called elementary matrix. Okay. So first thing to note is when I, let me write indices because I want running indices. So I will write PRS. So R and S, they are in between this. This is En plus AERS. RS's entry is A and everywhere else it is 1. So first thing to note is, if R is less than S, what did we do here? This is once on the diagonal and A somewhere. A can be here or here. So if the row S is bigger, then it is upper triangular. Because this is rth row, this is rth row, this is sth row. Then we are adding this one in the essay throw, this picture is not very good. So let me rub and draw it. So this is the matrix, ones on the diagonal, and S, suppose it is later than R, then this is the diagonal entry S. If R is here, we are not changing SA throw, we are changing RA throw. This we are adding it here by multiple of A. So it becomes upper triangular. Similarly, if R is bigger than S, then it is lower triangular. So these elementary matrices are either low triangular, and we never allow R equal to S. R is not equal to S. R equal to S will mean we don't allow R equal to S. So these matrices are upper triangular or low triangular, and the diagonal entries are always 1 with diagonal entries, with all diagonal entries 1. Such triangular matrices are also called normalized. Normalized triangular matrix means either it is upper triangular or low triangular, and all diagonal entries of that matrix are 1. Okay. Also, they are clearly invertible. See, these matrices are invertible because diagonals are 1, and we have seen such matrices are invertible, and they are also, again, if originally the upper triangular, this is also upper triangular, and it's a low triangular, then it is low triangular. So the inverses, in fact in this case we can write down the inverse very well. So let me write it down. So what is the inverse of BRS? This inverse is nothing but BRS minus A. This is the inverse. You can just compute. See, for example, if you want to prove this, the way to prove this is look at En plus A ERS, this, and multiply En minus A ERS and compute this. You will get identity. That means this guy is the inverse of this. And this computation you do it like what I said. That's it. Okay. More generally, you can also write down a formula like this: BRS A times BRS B. This will be nothing but BRS A plus B for any scalars. Remember, R is not equal to S. So this means what? This means these matrices you can think, this means it's a group homomorphism. This means the following. I want to put in a little bit fancy language. Let us take the additive group of the field K plus, and then take G L N K. This is the group of invertible matrices of order n. This is the units in this ring, and we have a Nash-L map for a fixed RS are fixed in between 1 and n, R not equal to S. Then we have a map BR here, BRS here. In A goes to BRS A. We have seen this matrix is invertible, and this what we wrote here, this equation says that this is a group homomorphism, because addition here will go to the product here. This is a group homomorphism. Okay. Okay, now I want to check the following. This is at least once we have to check. if I multiply a given matrix A by B, R, S, A on the left side, it is like obtaining from A, when you go here, that is like changing the rth row of the matrix. So, rth row of A. This rth row, that is R, let me write it rth row here, RR. And here the new rth row will be rth row of A plus A times sth row of A. This is what will happen to this new matrix. And let us check this. Rth row is the vector. If you call this matrix as Aij, I am checking once. This is A, R is fixed. So, Rj, this is the rth row. J is from, let me call J in I. If you like, I is our set 1 to n. This is the rth row. And what is this row? Write down this first. Rth row is Arj, J in I, and this one is plus A Rs, that is Asj, J in I. But they are added like this. Arj plus A is component wise, Asj. This is the new row of this new matrix. And what did we do? From the rth row, so rth row is here, A, R1, A, R2, A, Rn, and sth row is, I am assuming S is bigger for simplicity, AS1, AS2, ASN. And we have multiplied this sth row by A and added here. So, this row will now change it to, this row will change it to this plus A times this. So, AR1 plus AS1, comma, AR2 plus AS2 and so on. ARN plus ASN. So, this is precisely this row. Watch it. J is varying here. So, multiplying A by pre-multiplying by this elementary matrix is equivalent to making a row operation. Similarly, I will say that if I want to multiply from the right side, that is like a column operation, and the proof is similar. Okay, with this, so all these operations, what do I want to do? I want to prove the following, and also the permutation matrices. So, to define a permutation matrix, so if you have a permutation of the letters 1 to n, then I denote P sigma. P sigma is a matrix. So, this is the matrix obtained from the identity matrix by permuting the rows. Rows according to the permutation sigma. And we want to say that this matrix is actually invertible. But that is again very simple, because what you do is, because permutations are in a group, so there is the inverse to permutation. So, there is a permutation so that sigma tau is identity permutation. So, therefore, we need to check the formula P sigma times P tau equal to P sigma tau, which is identity, the P identity. P identity is identity matrix. So, that means this is the inverse of this. So, that means we have proved that P suffix sigma inverse is P sigma and then the inverse of the matrix. So all these matrices are invertible. So that means P sigmas are actually invertible matrices. And not only that, we have a nice group homomorphism Sn to Gn, Gl and K. Sigma is mapped to P sigma. This is a group homomorphism, where operation here is composition, operation here is the matrix multiplication. So, okay. So, let me come to the main theorem which I would like to prove. I think I will see where how much we can prove today. So this is a theorem I want to prove. Okay, A is a matrix M N K of rank R. And let us put minimum is equal to K. Okay. Then there exist elementary matrices many of them. So B1 to BP. Elementary matrices are always square matrices. So they are in M, M, K. And also C1 to CQ, they are in M, N, K. Such that if I multiply A by this, pre-multiply A by these B's, so B1 BP times A, and from this side I multiply by C's, C1 CQ. This product is a diagonal matrix, DAG D1 to DK, which is this matrix is this. I have written diagonal, but it is a matrix here. So that means depending on whether M is smaller or N is smaller, then this diagonal matrix will look like so. Where with I can also arrange that D2 onwards, D2 to DK, they are all 1. D2 to DR, sorry, R is a rank. D2 to DR is 1, and DR plus onwards up to DK they are 0. If moreover, if the rank is full and it is equal to N, then we don't need C's, we do not require the matrices C1 to CQ. This is very, very important theorem, and I will show you many, many applications of this. Okay. So let us start proving it. So proof. First let us see what we want. So we have given a big matrix A11, A1, N, AM1, AMN, and in between also. So AI1, AIN, A1J, AIJ, and AMJ. And what do you want to bring? You want to multiply from this side and that side, so that the matrix becomes like this. Somebody here, that is D1. Then 1, 1, 1, 1, 1, 1. So many places. Total R. This is R cross R matrix. Then zeros. And depending on whether your n is smaller or m is smaller, this is the main diagonal, right? So this is in the picture I draw, there the columns are more. So in this, m is smaller than n. Otherwise it will look like, so now in the other case, it will look like D1, 1, 1, 1, 1, 1, and then it will hit the other side faster. And then there is still, so there is 0 here, 0 here, there is 0 here, 0 here. So that is what we want to achieve. And what are we allowed? We are allowed to make row operations and column operations. And whenever we make a row operation, we multiply from the left. Whenever we make a row operation, column operation, we are multiplying from this. Or also you are also allowed to change the rows and columns, right? But I don't want to use that multiplying a matrix by a non-zero row by a non-zero scalar or column by a non-zero scalar. This operation I don't want to use. Only 1 and 3 is I want to use. So already in a Gauss elimination, what did we do? So by changing the rows and columns, interchanging, we have brought this element non-zero, and then we have used that to kill down everybody and so on, right? And then we did this. Okay, so and already then if you use those operations, then we already get a matrix in this format. C1, C2, CRR, and zeros below everywhere here. 0, everywhere 0 here. Here also 0, and there are some stars. Somebody here, some stars are. This format we always bring it like a Gauss elimination. We make this we bring this entry non-zero. As far as possible, we use the rows and then kill the entries below that by using that row and elementary operation. Similarly this, and once you have done for this block, then already we know the rank of these matrices are, and these rows are linearly independent, and therefore columns are also linearly independent, and therefore all these guys, the below here cannot be non-zero, because if it is non-zero the column rank will go up, but we already proved column rank is row rank and so on. So already this we can achieve where Cj's C let me call C11, C22, CRR is 2. So Dj I am calling Cjj, from J is from 1 to I. This is already achieved. Now what do you want to check? Well, I wanted to check, therefore this matrix is, I will correct. So this is D1, Dr here, this is 0 here, and somebody here. First of all, note that Now when I use backward row operations, I will kill all these guys because these are non-zero. So all these I will kill. This is 0, and here now I start using the columns. Already the below that was zeros. So I will start using this, and it becomes 0 here. All these 0, this everything 0. So I actually got a diagonal one. But now only interesting thing is I want to push this up. I want to this dr. I want to transfer this matrix by again elementary transformation, so that this becomes d1 to dr minus 1 and dr, and this becomes 1. So slowly by induction I will push the diagonal entries to the upper diagonal entry. This is what is the only non-trivial part here. So that is, I have written down that. Exactly. So that is very worth noting it. This is the most important step, which is, so it only thing happening at this level. So I will only write 2 by 2 picture. This is dr minus 1, this is dr, this is 0 and 0. And our problem is to arrive at dr minus 1, 1 and 0, 0. This is the problem. So what do I do? So this dr is, both these entries are non-zero, that we know. This is non-zero. So I am going to multiply this row by 1 over dr and add it here. So what will I get that way? I will get this row will not change. So this will be as it is. And this will become, this will not change, this will become 1 here. So from here I want to kill this guy, this dr. So that means what should I do? I should multiply this row by dr and subtract. So this will not change, but this will change. So what will it change? This change to dr minus 1, 1, this will not change, and that will, I have to multiply this by dr and subtract. So this will become, yes. So what will it become? 1 minus dr times, no, I do not want to make it 0, I will first make it 1. I want to make it 1. How do I make it 1? This I want to make it 1. How do I make it 1? You multiply this row by 1 minus dr and add it, right? So this is what we do. I made it 1 here. So I multiply this row by 1 minus dr and add it here. It is this. Now we want to remove this 1. So subtract it. So this will become, this will not change now. 1 minus dr times dr minus 1, 1, and this I wanted to make, so I just subtract it. So this I have to subtract. So this will get cancelled and this remains there with a plus sign. See, I managed this here. Now I have to get rid of this. So that is, now what do? You multiply this by 1 minus 1 over dr. So that is same as dr minus 1 by dr. Multiply this by that and add it here. So when I add it here, this one and this one has negative sign. So this, when I multiply this by this first, the denominator will go, numerator will be dr minus 1 and multiplied by this. When I add it here, this has the opposite sign, so it will get cancelled. So, you precisely get this. See, when I multiply this row by this, first dr will go away, then this times dr minus 1 remains, this nothing happens here, and when I add it here, this one and this one has a different signs. So, they will get cancelled. So, I get this, that is it. So, that is how we get the diagonal matrix of the required form. Okay.